Welcome to Chemistry Lover, and let us solve our previous challenge question. So this was our question. You can see you have to tell which compound will react faster and what is the major product for these two reactions. Now these are cases of simple SN2 reactions, but there is a trick involved, and that is the main point of this question. So our first molecule was this one, PHS ethyl group, then PH, and here you have a plus charge because sulfur is it is tri-coordinated. Now both molecule, you can see this molecule and this molecule, they are basically the connectivities are almost same. One ethyl group is there in both cases, and other is aryl group. This side aryl group, here also this is some benzyl group. Okay, so connectivities are same, but now so why is the difference, or is there any difference, that we have to see. So here you can see this reaction is pretty simple. NCS minus, this is a nucleophile, it will attack at the benzylic position to give you the SN2 reaction. So here the product is PHSCN plus PHS ethyl. Okay, this is the product. So this is the first product here. So this is product A of your reaction. Now this reaction is going through SN2 reaction. Now you can think another attack at this position, you can see. So you may think another attack can occur here. It will occur and it will give you a small product, I mean the minor product, which is this. So SCN, this will be minor product. Along with that, this PHS pH. Okay, so these two are there, so but they are these two are minor, these two are actually major products. So this is our product A. Now what about the other? And now the question, why this nucleophile is attacking over here and not over here? So the reason is simple, because here whatever the transition state is, when the attack is taking place over here, whatever the transition state is, that is stabilized by the presence of this phenyl group, the aromatic ring. So the transition state of SN2 reaction looks like this. So let's say you have this this is your transition state, any transition state of SN2 reaction. Okay, now this is your carbon atom which is undergoing the substitution reaction. This is your nucleophile, and this is your leaving group. Okay, so in this case all these things are, what are they? So here this nucleophile is this thing, this leaving group is this whole thing. If we are talking about this, then this whole thing is your nucleophile, and this is the carbon atom, this carbon atom. Now here you have this phenyl group, right? So here you have this phenyl group, here you have this phenyl group, and now you can see here all these p orbitals are there, right? So these p orbitals, you can see they are actually parallel with respect to this orbital. This orbital which is developed in the transition state, you can see this nucleophile, this carbon atom, and this leaving group, this orbital, and this is parallel with this set of p orbitals, right? So there is a overlap among all these orbitals, and this overlap is actually stabilizing the transition state. But same kind of overlap cannot occur when the attack takes place at the ethyl group, simple ethyl group, because there is no such p orbitals or no such pi orbital set which can stabilize the system. That's why the attack is taking place on this center and not on this center. Okay, now what about the next thing, I mean the other molecule? What about the other molecule? So the other molecule is this one. Other molecule is this one, where you have this sulfur and this ethyl, this plus charge. Now here again this S ACN minus, it can attack either over here or it can attack over here. And you can think that when it is attacking on this center, same kind of stabilization can happen from this pi orbital set, which is not possible when the attack is taking place here. But here is a trick, or here is a twist. What is that? That is, this system is not a open system, this is a cyclic system. This is not a cyclic system, this is a cyclic system, and that's why this position cannot become this kind of linear. Okay, this position cannot become linear, as there is a this is a cyclic system and there is a strain. So if linearity cannot be attained, then this kind of overlap can also not occur. So that pi stabilization is absent here. Okay, on the other hand, if this ACN attacks over here, then linearity is attained, although there is no such pi stabilizing group, but at least the linearity is attained, the linearity in the transition state. Okay, but this linearity cannot be there in case of attack on this side, and that's why the transition state is somehow strained. Okay, but this transition state is quite free, and that's why most of the nucleophile will attack on this position. So here you will get a different product. Here you will get this plus pH SCN. This is your so this is your product. Okay, so this is your product B. This is your product B. Okay, sorry, not pH here. You don't have pH, you have ethyl group. Okay, so this is your product B. This is your product B. Here a very little amount of ACN will also attack over here, and you will get a minor product, but the major product is this one. So our option 4 is our correct option, and actually I put option 4 and 2 actually same, and they are the correct answers. Okay, so our product A is this one, our product B is this one. In first case, because of pi stabilization, the attack will take place on the Benzeli position, but in the second case, pi stabilization is not there, so attack is not taking place at the Benzeli position. So that's all for this video. Thank you for watching.